All right, so here's my squid. The squid shoots up, if it wants to go, say, this way, let's say it wants to move this way. If it's going to go down, which way should it shoot water out of its jets to get it to move? What direction? Let's say it could somehow shoot water in any direction. Somebody tell me, which way should the squid shoot water if it wants to move this way?
Up.
Yes, that's correct. It should shoot water out this way. And so the resulting force will push the squid down in this direction. All right. What if the squid wants to go up into that way? Which way should it shoot water?
Down right.
Yes. Okay. So the squid pushes water out this way, and that makes it move in the opposite direction. All right. So let's say a bobsled is going down a hill, and you can't ignore wind resistance. Draw all the forces on the bobsled. All right. So let's say here's our bobsled. I love bobsledding in the Olympics. It's fun. It's full of lots of physics. All right. So here's our bobsled. There's our guys. All right. So what are all the forces acting on our bobsled? Because there's going to definitely be, you're going to need to draw force diagrams on the test. So so you better know how to draw all the force diagrams. Okay. All right. So what forces are acting on our bobsled? Let's say you can't ignore wind resistance once it starts to move.
Normal force and gravity.
Yes. We've got our normal force going this way. That's our normal force. And which way is gravity going? Well, it's going that way, right? So M times G, that's our normal force here. And let's say we have some angle theta here. How do I find my normal force? If I have what's the formula for the normal force?
Mg cosine theta.
Yes. So the normal force is equal to mg times cosine of theta. And so it would be equal and opposite to this force going this way. Here's the hypotenuse of our triangle. And then this would be our angle theta. Okay. So that's our normal force. Which way is the force of friction pulling on our bobsled?
Is it moving at this point?
Yeah, let's say it's starting to move.
It's going upwards.
Oh, well, let's say the bobsled's going that way. Oh yeah, it's going upwards. Okay. So the force of friction is going up that way. We'll call that, there's mu friction, mu K. Which way is the force of drag going? If we have drag on the bobsled.
I'll say up as well.
Yeah, the friction and drag force always oppose the motion of whatever it is. So drag is also going to be going this way. All right, and which one do you think is higher? The force of friction or the force of drag? Which one is used probably higher?
Force of friction.
Yeah, probably the force of friction is going to be higher. Okay. All right, so we've got the force of drag is pointing up this way. We've got our force of friction going up that way. And then we've got our force due to gravity, which is making it accelerate. How could we find the force F of X here pulling it down? What would the formula for that be?
Mg sine theta.
Yes. Mg sine of theta. Okay, and that's our force going down that way, and it's going to be this part of our triangle. We got a right triangle right there. That's f of x. And then here's our normal forces opposite to this one. Okay. So, all right, we got the force of drag. So if there's a skater on a pond and there is friction, okay, let's say he has an initial velocity. How far could he travel before it stops? So it could be an ice skater. I guess we can go with this example of our bobsled, right? Once the bobsled gets, let's say, gets on a flat spot. Here's our bobsled, right? So once the bobsled is on a flat piece of ice here, okay, there's some friction. There's a frictional force. Oh, I'll call that mu. There we go. All right. And what is the force of friction equal to? We said it before. It was mg times mu k, right? And then what is our how could we find our acceleration from this force? That's supposed to be mu k. So if I said, what is the acceleration now? What would you say? So this is our force due to friction. I can't write it. There we go. How would we find our acceleration now? What do we always know that force can be? What formula?
Mass times acceleration.
Yes. So mass times acceleration, then the masses cancel out, and we just have the acceleration is equal to g times the coefficient of kinetic friction. Why doesn't the mass matter? Why doesn't the mass? Maybe that was shocking. Why doesn't the mass matter? Well, we can say that it cancels for one thing. The mass just cancels. And we can also say that when things are, oh, this is a good question. All right. If I drop a bowling ball and a penny off of the Empire State Building and we ignore wind resistance, which one will hit the ground first?
They'll hit at the same time.
Yes, that's right. They will hit at the same time. So the mass of the sled apparently doesn't matter because things they fall at the same rate. Okay. So what about if I dropped if I dropped a squirrel and a human out of the airplane? And we didn't ignore wind resistance. Which one would hit the ground first if they don't have parachutes? I would never do that, but which one would hit the ground first? Let's talk
Sorry,
about
could you repeat the question again?
Yes. What if a squirrel and a human fell out of an airplane? So here's my human. It's a weird human. And I had a squirrel like this, my little squirrel here. Okay. He's got a big tail like this. If I drop him out of an airplane, which one's gonna hit the ground first, do you think? Well, what's the formula for the force of drag? Does anybody remember? What's the formula for the
I know the area should be in the formula, but I can't remember the full formula.
All right, it is rho times the area times the coefficient of drag times v squared, and it seems like there should be a 1/2 in there.
There is.
There is? Okay. I just had a feeling that there should be a force. Okay, so it's 1/2. Yes. 1/2 times rho times a times c times v squared. Okay. Now, how do we find their terminal velocity? All right. So what we do is we set this equal to m times g, right? So we set this equal to m times g, and then we solve for v, because here's our force due to gravity. So we say the force of gravity, when the force of gravity equals the force of drag, that's when we hit the terminal velocity. And so the terminal velocity v will equal m times g. This will be the square root times 2 divided by rho times AC. All right, so humans have a terminal velocity of about 34 meters per second, and squirrels only about 12 meters per second, because they're much lighter. And so they don't, and when there's drag, then the mass kind of matters a little bit. So humans, because we're heavier, we will fall much faster. All right, but this is how you find the terminal velocity. Okay. All right, so let's move on here. All right, so we talked about drag force. You should know about the force of friction, so both kinetic and static friction. All right, you should know about pulleys. So there was the problem of the Jeep. Why did having a pulley attached to the winch, why did that allow, how did that create more force on the Jeep? All right, and then let's go over here. Let's say you have a pulley, and you have 2 equal weights attached to the pulley. Okay, so let's say the weight of these is 60 newtons. What is the tension in the line going to be here?
60 Newton.
Yes, it'll be 60 newtons. Okay, and it's also going to be 60 newtons over here. All right, what if we have one mass over here? This is 60 newtons, and this is, let's say, 20 newtons. Which way is this going to fall?
To the
To the
left.
left.
Yeah, it's going to go down this way. Okay. And what's going to be, let's draw a force diagram for this. What's the force? What are the forces acting on this one?
The weight.
Yeah, there's the weight. There's m times g. And
That's tension.
yes, there's tension here. Is the tension the same over on that side?
It should be.
Yes, it better be the same. Because our rope is not stretchy. All right. So then what are the forces on this one?
It's weight as well.
Right. So we'll say this is m2 times g. This will be m1 times g. All right. So how could we find the total acceleration on our system? We know which way it's going to accelerate, but how could we find our total acceleration?
Set them equal to mass times acceleration.
Yes. All right. So we know that the total thing is going to equal our F total. Okay. So that'll be F total, right? And then what did we set that equal to?
Could you do the forces on like the first block plus the forces on the second, or like minus the forces on the second block?
Yes, that's right. So we'd have F1 plus or minus F2 because it's going the opposite way. So minus F2. All right. And that, yeah. So that'd be the correct way to set up that problem. But I don't think you had a problem like this in the homework, did you?
No.
Okay. Let's see what else. All right. So you should know there were a couple problems with pulleys. The ones that you should look at were well, I think yeah, 5.81, 5.84. Actually, just look at the problems in the homework that have pulleys in them, and it'll be similar to that one. All right. Then for the last part, let's see here. If we have a crate on an inclined plane. Oh, actually, there's one other problem I wanted to talk about. This is an important problem. All right. So let's look at this problem here. All right, let's say a drone is flying. I'll draw another picture on there. All right, so here's a drone. Let's say in the future that Amazon has drones delivering packages, all right? And your house is right here. Here's your beautiful house, okay? And let's say that the drone is flying this way with some constant velocity. And let's say it's 100 kilometers an hour. Wow. All right. So Amazon has these drones in the future and they fly around and deliver packages to your house. All right. Let's say the drone is flying 100 kilometers an hour and it has a height of 500 meters. Wow. Wouldn't this be cool? Imagine you can order socks off Amazon and a drone will fly them to your house and they'll be there in under 15 minutes. Isn't that amazing? Okay, so this thing is at 500 meters. It's going 100 kilometers an hour because it doesn't have time to slow down to get everyone's socks delivered on time. And so it's going to drop this package here and it's going to land right on your doorstep. What do you guys think? Is that a good idea? So does anybody think it's a good idea?
It's a horrible idea.
Well, maybe it's a terrible idea, but all right. So there's a couple questions. Okay. So if it's going 100 kilometers. Oh my God. All right. How far does it need to drop the package from your house? What's that distance? Okay. So figure that out. It's 500 meters up. Okay. So what's this distance here? And another, so here's the package. Okay, the package is coming in hot. There we go. Welcome to the future. All right, there's your package. Hopefully it's not your PS5. I guess you could have there, we'll write PS5 on it. In the year 2025, PS5s become widely available. You order it off Amazon and your drone launches it like this. Isn't that great? Okay. So your PS5 is going to be dropped there. How long will it take for the PS5 to hit the ground? How many seconds? What's the time? All right. So how would we solve this problem? All right. So what's the first step to do? We know that what's the y velocity of the package initially? Because here, at first, the drone is clutching your PS5 with an electromagnet. There we go. All right, so it's got your PS5. What's its initial y velocity?
Sorry, could you repeat the question again? You cut off for a second.
Oh, sorry. All right, so what's the initial y velocity of your package?
Zero.
Yes. So the drone it's flying this way. So its initial y velocity is 0. How could we calculate how long it will take for the package to hit the ground? Oh, sorry, go ahead. What?
Let's use the kinematic equation.
Yes, which one should we use?
I guess one with delta t.
Yes. But which one? All right. Well, it's y.
The second.
Oh, I don't know which one the second is, but it's y equals 1/2 a t squared. Okay. So we know what the height is here. Our y is going to equal 500 meters. Okay, 500 meters, and we know what a is, so now we can solve for t. So a is 9.8 meters per second squared. Okay, and so we can plug all that in there, and we will get t is equal to it's going to be 2 times y over a, and it'll be the square root of that. Okay, so that we'll put the numbers in. T is going to equal 2 times 500 meters, right? Divided by 9.8 meters per second squared. All right, so how can we find this distance here?
Can I ask you a quick question?
Yes, absolutely.
So if you had air resistance or anything like that, would you just solve for acceleration first and do force equals mass times acceleration, and then you'd plug that into the kinematic equation?
So wait, you're saying if this problem had wind resistance?
Yeah, or something like that.
Wow, yeah, this would be trickier if it had wind resistance. So you'd have to solve for your acceleration first. So it'd be gravity minus the force of drag, although it's a little bit tricky in this problem because your velocity is going to, since the velocity is changing, the force of drag is also going to change. So I'd say for this problem, we're not going to worry about wind resistance. Because if you put drag into this problem, then it becomes a lot trickier because the force of drag is constantly changing. Drag is not a constant force because, so FD here equals 1/2 times rho times A times C times V squared. So the thing about drag is that if your velocity is changing, this is not a constant force. So for the purposes of this, we're going to neglect wind resistance because that is a much tougher problem, and probably I think for an hour exam, we're not gonna go down that road.
Gotcha. Thank you.
No problem. But there could be a problem where I ask you to calculate something's terminal velocity, because when you hit terminal velocity, then what happens is the force of drag is constant, and so then you can calculate it easily. But until you hit that terminal velocity, the drag force is changing, and so it's always increasing. So for the test tomorrow, if there's a problem like this, you're not gonna need to worry about drag. So no wind resistance for this one, so no drag. Okay. All right. So once we know the time, which equation could we use to solve for the distance it would travel?
We could use distance equals to initial velocity times time.
Yes. So x equals v0x times t. All right. We know what t is, so we can plug that in there. And the package had an initial velocity of 100 kilometers per hour. So you'd need to convert that into meters per second, and then you could get the distance here. Okay. Now, last thing is, what would be the magnitude of the velocity when this thing hits the ground? How could we find the velocity of the package? All right, so let's draw a picture here. All right, so our PS5 it's moving. Well, I guess in the future, Amazon will have some really amazing bubble wrap. And so you don't need to worry, because your PS5, it's just going to bounce harmlessly. There we go. See, there, your PS5 is safe. Jeff Bezos would never let it be destroyed. All right. So if we want to find its final velocity when it hits the ground, we need to know its final x velocity, which is the same as its initial velocity. So that's going to be 100 kilometers per hour. So once we know that, then we need to know its final y velocity. How could we get that one? What is v y final? How could we solve for that one?
We could say Vy final is equal to U plus, initial velocity plus acceleration times time.
So yes. So V0 y, or V initial, minus AT, right? And what's its initial y velocity? Well, that should be 0, because it didn't have any initial y velocity. So we can say VYF equals minus AT. Okay, and the minus sign should go away if you call down negative. And so you can get its final y velocity here. Then for the velocity, okay, you can say that its total velocity is equal to VFY plus VXF, and these are squared. All right, let's see if there's anything else that we should talk about. I think that's probably everything. That's, yeah, as so that is, I don't think that's all we're gonna have time for tomorrow. And I'm gonna there should be about 12 questions, between 10 and 12 questions. And my goal is to, on average, the average time will be maybe 40 minutes. So some people will be done earlier and some people will be done later. Okay. And if you show your work and hand that to me, I will give you partial credit on the exam. So make sure that you do that. All right. Are there any other questions?
Do we need to know drag coefficients?
Oh, you mean like memorize them for different
Yeah.
objects?
Yeah,
No, I'll give you that.
thank you.
If you need to know a drag coefficient of something, I'll give that to you.
Oh, can we also make a piece of paper with formulas that we need?
Oh yes, yes. Please make a 3x5 note card. Thank you for reminding me that. And you're allowed to bring a 3x5 note card to the exam. You can write anything you want on it, front and back, but it has to be handwritten though.
Thank you.
All right. Any other questions? All right. Well, I guess if nobody has any other questions, then that's basically it. So just review the homework and then the things that we talked about. And I will put my notes. I'm going to take pictures of them and I'll put them on Pearson. All right. Well, if no one has any other questions, that's it then for the review. All right.
you.
I'll see you guys tomorrow at 10 o'clock.
Thank you.
Thanks a lot.
Bye.
See you tomorrow.
you.
Thanks.